In this second video, we're going to derive an astonishing result in complex analysis, Cauchy's theorem. For some complex function f that is analytic on and within a closed contour C, we will show that the associated contour integral vanishes. And this derivation is going to make use of the Cauchy-Riemann equations that we derived in topic 3 for complex analytic functions. First of all, there's a quick recap of what we covered in the previous video. We saw how to parameterize integration paths using a single variable t. We introduced the concept of a contour integral. That's the integral of a complex function along a path in the complex plane. And we showed that it's possible to think of such contour integrals as a complex sum of real integrals. We did that by breaking up the complex function f into its real and imaginary parts u and v, and also considering the line element in the complex plane in terms of its real and imaginary parts. We also looked at how to bound the magnitude of a contour integral, and we did that by considering the length of the contour in the complex plane, and also the maximum value that the magnitude of the complex function achieves along that contour. These are the intended learning outcomes for this video. After watching this video, you should be able to derive Green's theorem. This is essentially the two-dimensional case of Stokes' theorem, and this relates line integrals along a closed contour to integrals across the region bounded by that closed contour. We will use Green's theorem and the Cauchy-Riemann equations to prove Cauchy's theorem. And lastly, we'll show that Cauchy's theorem can be used to show that the integral of an analytic function depends only on the endpoints of the path, not the details of the path itself. With that, let's begin.
We're going to cover an amazing result in complex analysis, Cauchy's theorem. Cauchy's theorem states, if f of z, some complex function, is analytic at all points on and within some closed contour C, then the following is true. The contour integral around this notation means a closed loop. So the contour integral around the closed contour C of f of z, which we're assuming is analytic, dz, vanishes. It equals 0. And this is an amazingly important result, so I'm going to put a red box around it. This is Cauchy's theorem. And we'll explore the consequences of this later in this video. First of all, let's prove it. We're going to do this using Stokes' theorem and the Cauchy-Riemann equations relating the real and imaginary parts of an analytic complex function. First of all, let's set out the problem. Let D be the closed region of all points on and within the closed contour C. I'll put a little picture. This is the real and imaginary axes, and our contour C is closed. Might look like this. That is C. We denote the region on and within C by the letter D. From the previous video, we know that we can write a complex integral of this form, like this, where we substitute in f in terms of its real and imaginary components, u plus iv, and we substitute the differential dz as dx plus I dy. Multiplying this out, we obtain a contour integral along C of u dx minus v dy plus I times the integral of v dx plus u dy. So this is a complex number where the first term is the real part, the second term is an imaginary part. But you'll notice that the integrals themselves, that I'm going to label I1 and I2, these are real. I1 and I2 are real integrals, and they're real numbers. And in order for Cauchy's theorem to hold, we want both of these real line integrals to vanish. So we have two line integrals we need to show vanish. To show that something equals 0, we need both its real and imaginary parts to be 0. We're going to do this using Stokes' theorem. Recall Stokes' theorem. Which is this. It's the integral around C of f dot ds. Here f is a vector field, which means that it has x, y and z components. It's a vector field. This is given by a surface integral of the curl of that vector field, dotted with some unit vector and an area element. Now Stokes' theorem relates the integral of the curl of the vector field on the right hand side over the surface D to the line integral of the vector field around the surface boundary C. Here n is a unit vector, normal to the region D, enclosed by the path C, and D has area element dA and line element ds. I'll draw a picture to make that clearer. This is some region in three-dimensional space, x, y, z. The region D might be described by a shape that looks like this. It has area element dA. It is enclosed by a path C, and it has line element ds and normal unit vector n. Right, so that's Stokes' theorem. We care about two dimensions. We care about the complex plane. In our case, we have the left-hand side, which is f dotted with a line element ds. This will give us the x component times dx plus the y component dy. We only have two axes of interest, x and y, so we neglect the term dz. This is what f dot ds gives us on the left-hand side of Stokes' theorem. On the right-hand side, the curl of the vector field, you will recall, is given by the determinant of this array. These are unit vectors in the x, y, and z directions. Now for I1 and I2, the unit vector n is simply the unit vector in the z direction, because the region D that we're interested in our complex integral lies in the xy plane. For the case we're interested in, the right-hand side of Stokes' theorem therefore has the curl of f dotted with the unit vector n, gives us the partial derivative with respect to x of fy minus the partial derivative with respect to y of fx. Plugging this into Stokes' theorem above, this gives us the special 2D case, which is called Green's theorem, which I'll write below. So Green's theorem. Green's theorem is that the integral along the closed loop C in 2 dimensions of fx dx plus fy dy is the integral over the region D of dx fy minus dy fx, and the area element is dx dy. And this is also important. This is Green's theorem. And what this does is it allows us to turn line integrals into surface integrals. We can apply this result to the line integrals that we're interested in order to prove Cauchy's theorem. First of all, we had that I1 is the integral along the closed loop C of u dx minus v dy. Looking at Green's theorem, we can identify that fx is u and fy is minus v. That means that through Green's theorem, the right-hand side of Green's theorem will now read the integral over the region D of the partial derivative with respect to x of fy, which is minus v, minus the partial derivative with respect to y. From Green's theorem, we need f of x, which is u, dx dy. And moving signs around, we get minus the integral over the region of dxv plus dyu dx dy. We next note that the complex function we're integrating, given by u plus iv, is by assumption analytic in D. Therefore, u and v in this integral satisfy the Cauchy-Riemann conditions. Satisfy Cauchy-Riemann. as a refresher, our first Cauchy-Riemann condition is that the partial derivative with respect to x of u is the partial derivative with respect to y of v, and the second one is this. So we're allowed to assume that these hold because by hypothesis our complex function is analytic in D. This means that we can replace the second term in our integral, dyu, as minus dxv. This will give us this expression. And now these terms cancel. Therefore, we have that the line integral I1 does indeed vanish. We can do the same thing to the second line integral, I2. I2 was given by the integral along the closed contour C of v dx plus u dy. Looking at Green's theorem at the top, we now identify f of x, fx as v, and fy as u. This gives us, through Green's theorem, the integral over the region D of this term minus this partial derivative dx dy. Once again, we can use Cauchy's theorem to substitute, to replace the second term in this integral. And that will give us dxu minus dxu dx dy. Therefore, this second line integral also vanishes. We had that our integral of interest f of z dz was given by I1 plus I times I2, and we've just proved that this is 0 for f analytic on and within the contour C. And that completes the proof. I'll make a quick note here as an aside that application of Stokes theorem actually requires the derivative of the complex function to be continuous. However, there are stronger proofs of Cauchy's theorem, CT, that do not require this. We're not going to go into such proofs, but you can look up, for example, the Cauchy-Gaussat theorem. What does Cauchy's theorem actually mean? We have that this integral around a closed contour C of an analytic complex function evaluates to 0. And a picture here might help. Here we have the real part of Z, the imaginary part of Z, and this is f of Z. Now the closed contour C in the complex plane might look something like this. And it will be traversed in the anti-clockwise direction by convention. And I've used this multicolored pen to emphasize that all of the points along this closed contour are themselves complex numbers. So as you go along this contour, the real and imaginary parts of the number at each point will in general be varying. Superimposed above this contour, we can depict the change in the complex function also by a multicolored line to emphasize that it also has a complex number defined at each point. The function might look something like this, where the height above the plane could represent the real part of the function value. If we consider, instead of taking the integral, if we take the discrete version of this sum, it's the sum of the value of the complex function at some point zi times a small length delta zi along that contour. This is a sum of complex numbers, and we know that we can treat that as vector addition. So we might have something like this, where as we're changing I, we add more vectors top to tail. And if we were to depict this on our diagram on the left, each of these arrows corresponds to the area given by multiplying together the height and width of these rectangles in the complex plane, where their heights and widths are both complex numbers. If we take the continuum limit of this quantity, we recover the integral that we're interested in. And what this means in the vector picture, the vector length approaches 0, but the arguments of the complex numbers conspire to make the total vector have length 0. So it might look something like this, where we started at this point, and as we added together all of the contributions and made them infinitesimally small, we end up back at the origin in the complex plane. And so the integral evaluates to 0. That this is one way of trying to picture what's going on in Cauchy's theorem. And it's an extraordinary property of complex analytic functions that means that this excursion ends where it began, and the integral evaluates to 0. What else does Cauchy's theorem tell us? Another very important point. Cauchy's theorem means that a contour integral does not depend on the details of the path taken when the integrand is analytic. It doesn't depend on the path, it only depends on the endpoints. And as physicists, this might sound familiar to us, where we call potentials that have this property conservative potentials. Let's draw a picture to explain the setup. We might consider having, in the complex plane, we have real and imaginary. We might imagine starting our integral at this point and ending at this point. And we can define this path, and call it C1, and also this path, which we can call C2. Let's define the integrals along these two paths. Let's define I1 as the integral along C1 of our analytic function f of z dz, and I2 as the integral along the second path, C2. What do we get if we take I2 minus I1? We put the integrals in. We have the integral along C2 minus the integral along C1. We can rewrite this where the first term doesn't change, but for the second term we can instead traverse the path C1 in the opposite direction. Accounting for the sign means that we flip the direction we traverse the path C1 in. I'll note that here, that we get this result if we traverse this path in the opposite direction. Of f of z dz. We can join these two paths together to make a closed loop, and the closed loop is going to be described by going along C2 from the start to the finish, and then returning to the starting point by traversing the path C1 in the opposite direction. And this is the integral along a closed loop of a complex analytic function, and by Cauchy's theorem we know that this vanishes. Therefore, I2 minus I1 equals 0, and hence I1 equals I2, which is astonishing. The integral for an analytic integrand does not depend on the path. We didn't say anything about the details of C1 and C2 in this calculation. Only the endpoints mattered. And this is a really remarkable result that you should remember and be able to show using Cauchy's theorem. That's the end of this second video of topic 5. And there's not much to recap apart from the fact that we've stated and proved Cauchy's theorem, which is a phenomenal result in complex analysis that says that if a complex function is analytic at all points on and within a closed contour C in the complex plane, then the closed loop integral of f of z dz along that contour vanishes. Next up is the third video of topic 5. Thanks for listening.